Welcome back to the energy conversion lectures. In this lecture, I will give some details about the impact of an air gap in a magnetic circuit. In some applications, the air gap can be part of the nature structure of the magnetic circuit. In other types of applications, the air gap could be added to the magnetic circuit as part of its design. Let's give some examples to these two cases. The first type of applications, such as electrical machines, the rotating part, which called rotor, is physically isolated from the stationary part by an air gap. Practically, the same magnetic field lines flowing through the magnetic material and the air gap. To maintain same magnetic field lines, the air gap will require much more magnetomotive force comparing with the core or the magnetic material. The second type of applications, such as reactor or inductor, the air gap is mostly added to avoid the risk of saturation that cause loss of permeability, increase of current, and loss of power in the magnetic circuit. Implementing an air gap in a magnetic circuit, adding additional reluctance to the magnetic circuit. This will extend the range of the excitation current before magnetic saturation occurs. To elaborate on this concept, let's look at this figure that shows the magnetization curves of two magnetic circuits, one with air gap and the other without air gap. It is very clear that the curve with an air gap has less slope comparing with the one without an air gap. The air gap causes an increase of the reluctance. That means a higher magnetizing current I is required to obtain same magnetic field density B comparing with the non-air gap magnetization curve. Basically, if you have a magnetic circuit and you need to apply high current or store high energy without the risk of saturation, you need to add an air gap to your design of the magnetic circuit. It should be noted here that abnormal operating condition can also lead to the saturation and cause damage to the magnetic circuits. Therefore, air gap can also be implemented to protect the magnetic circuits from the saturation and abnormal conditions. To understand how the magnetic field behaves when there is an air gap in a magnetic circuit, let's assume we have the following magnetic circuit that consists of a magnetic core and an air gap. In previous lectures, we assumed that the magnetic field lines are confined and uniformly distributed within the magnetic materials and the air gap. Therefore, the cross-section areas of the magnetic field densities of the magnetic material and the air gap are same. In other words, AC equal to AG and BC equal to BG. If you remember, because of these assumptions, we were able to represent the magnetic field lines of the magnetic circuit by the mean magnetic field path phi. In practice, the magnetic field lines phi that flow through the air gap is spread out as shown. This behavior, known as fringing of the magnetic field lines. The fringing behavior causes an increase in the effective cross-section area of the air gap. In other words, the cross-section area of the air gap will be greater than the cross-section area of the magnetic material, or Ag greater than Ac, and therefore Bg less than Bc. It should be noted here that if the air gap is very small, the fringing effect can be neglected. Therefore, we can assume that Ag equal to Ac, and therefore Bg equal to Bc and equal to phi over Ac. In practice, if we need to add an air gap to a magnetic circuit, the air gap will be divided into several small air gaps to reduce the fringing effect. Now let's assume we have these two magnetic circuits and try to determine the excitation or magnetizing current I for both circuits. As you can see, circuit A is implemented without air gap, and circuit B is implemented with a small air gap. Since the magnetic field density B is known and equal to 0.6 Tesla, the magnetic field intensity Hc for the soft cast steel core can be determined for both circuits from the BH curve, and it is equal to 325 ampere turns over meter. Let's start with the circuit that has no air gap. The excitation current can be determined as follows, and it is equal to 0.328 amperes. Using the same procedure, the excitation current for the magnetic circuit with air gap can be determined as follows, and it is equal to 5.1 amperes. Actually, I provided this example to highlight the following 2 points. The first point is that the magnetic circuit with the air gap will require higher current of 5.1 amperes to achieve magnetic density of 0.6 Tesla. However, the magnetic circuit without air gap will require only 0.328 amps to achieve magnetic density of 0.6 Tesla. These results confirm what I have explained at the beginning of this lecture. The second point is that the magnetomotive force of the air gap of circuit B is equal to 1909.8 ampere turns, while the magnetomotive force of the magnetic core of the same circuit is equal to 130 ampere turns. That means even with a small air gap of 0.4 cm length compared with 40 cm core length, most of the MMF or magnetomotive force is used at the air gap. In other words, most of the energy is stored in the air gap. Now let's conclude this lecture at this point, and we'll continue in the next lecture. Thanks for your attention. I am Ihsan Al-Nabi, and it was a pleasure sharing this lecture with you. Thank you.